Hello everyone, welcome to the Statistical Foundation for Big Data Analysis. We will continue with module 2, which is our first module on statistical inference, and we will actually continue with this topic of likelihood that we started in last lecture. Just to quickly review, in last lecture we started by quickly reviewing the unbiasedness that we defined in our first lecture of point estimation, where we actually defined what is an estimator, and we actually discussed one of the various desirable properties of estimators. So frankly, just to tell you something, because what we are targeting is to predict certain aspects of population based on particular sample. There will be various approaches, various ways to give an estimator for that target, or formally speaking the population parameter based on sample. Now unfortunately, there is no one uniform best method of targeting a parameter, estimating a parameter. Between two estimators, some will have certain qualities more than other estimators, maybe the other one will have certain other qualities more than the first one. So in fact, this we will see, this comes very much in the setup of machine learning, which is ubiquitous in analyzing big data, that given an estimator, you will get into this kind of two sources of errors will become very common, like one will be bias and another will be variance. I mean, variance, not exactly this variance, well, this is only, but in a slightly different context. For every estimator, you will have bias as well as you will have variance. Bias, as you can see, the name indicates is related to what we are saying, that something is called unbiased if expected value of the estimator is the target parameter, and basically the squared difference between the expected value and the parameter value is called bias. So, and then there is another thing that is called variance. So often what will happen, you cannot reduce both bias and variance for a particular estimator. You have to come up with a balance. So this indicates that there are multiple desirable properties. Not everything can be achieved by every estimator. So unbiasedness was one such property. So if I draw a picture of a population, let's say a two-dimensional population. So this is your population. Let's say this population is this big cloud. Each point represents a potential or represents a member of that population. Now this is the center of the population. If you want to, the intuitive understanding is that, if you draw a sample which is sort of representative, the center of the sample should be same as the center of the population. So if this is your sample, so this big thing is population and this is your sample. So if the sample is representative enough, the centers should match. That was essentially the philosophy and the motivation for unbiasedness. We saw that sample mean tends to be an unbiased estimator of population mean. This was demonstrated in the finite population scenario and also in any general population. We saw that this is for the Bernoulli distribution as well as the normal distribution. We also saw that it's actually independent of distribution. As long as x1, x2, xn IID with same population, same mean, IID with same mean, the x bar will have mean same as the background population mean. From here, we basically moved on to something called likelihood estimation, and we defined likelihood estimator by, we introduced it by motivating the likelihood through this examples of coin. So okay, we also, just to give you a quick glimpse, we also discussed the variance situation, and we discussed that the population variance has an unbiased estimator, which is not the usual intuitive sample variance, but you would need this 1 over n minus 1 there to get an unbiased estimator of population variance. Now, so from there we moved on to likelihood estimation, maximal likelihood estimation, and in general the notion of likelihood. So likelihood basically is probability upside down. We said this last time. likelihood the main theme of last talk and this talk is probability upside down. So basically what likelihood approach does, based on certain observation that you have background population, you have drawn a sample. Now you can see the sample. Population is generally determined by certain values for some probabilities. For example, when you are talking about a coin tossing, remember population was all possibilities. So if a coin has head probability P, population is all possible tosses, potential all possible tosses in past, present, future of that coin with head probability P. Now population, this all tosses, like which one you will get head and which one you will, what proportion you will get head, what proportion you will get tail, etc., will be determined by this head probability P. Now head probability half gives you one particular population, head probability 0.1 also gives you another particular population. So if you know the population is coming from toss of some coin, still you don't know everything. This particular head probability determines the population. The goal of likelihood is to guess that head probability or determine which head probability is most likely. For example, if you have tossed a coin and got just an head, between these two, which one is more likely? We discussed this in terms of this motive example. When you are a detective, you are trying to solve a, find a criminal who has committed a murder or some crime. You start with trying to understand who has the best motive. Now, if you have observed a head in one toss and your options are head probability 0.7 and head probability 0.9, which scenario is more likely to give you a head in a toss? Obviously 0.9, because that scenario gives you more probability of getting a head in a toss. This was the philosophy of likelihood. We demonstrated this with some more examples of coin tossing. If you got 100 tosses and got 90 heads, head probability 0.8 is obviously more likely than head probability 0.2. Similarly, for these other cases, head probability 0.5 is more likely than head probability 0.2 is more likely than head probability 0.5. If you did 10 tosses and got only one head, the other scenarios were also there. From there, we moved on to define the likelihood. So we first defined it for absolutely continuous random variables, where probability is computed using density, probability is computed using integral. So basically, when you are computing probability using integral of a particular function f theta, so x1, x2, xn, we'll come to the discrete in a second, x1, x2, xn, IID with same distribution as some random variable x and for some theta and all subset A of real numbers, probability x belonging to A is integral over A of f theta x dx. Suppose we know this. Goal, guess theta based on x1, x2, xn. The discrete analog of this was you have done 100 tosses, got 90 heads, let's say, apart from 10, 20, 10th 20th, 30th, 48th, 58th, 68th, 78th, 88th, 98th and 100th. These tosses are tails, every other toss is head. So, if you are denoting x1, x2, x100 where each xi takes value 1 or 0, apart from x10, x20, x30, x40, x50, x60, x70, x80, x90, x100, all other x takes value 1 and these multiples of 10, the x's take values 0. If that is your data, based on this data you are trying to guess what is the head probability P. Now, of course, there are various ways to guess it. One approach will be which one is more likely, another approach will be just based on this data guess one value. We are now doing point estimation in this talk. We will come to the other version, choosing between two things later. In point estimation, we will try to directly guess a value based on this data. Now, this is the approach for likelihood. In case of density, where integral you calculate probability using integrals, the likelihood function was defined by just the product of these f thetas, because f theta x is basically f theta x dx was approximately probability x is near small x. So, observing this particular values, the probability of observing x1 equal to the particular value you got will be more if this f theta x1 is more. Observing the value of xi, the xi you observe will be more if f theta xi is more. So, if you take the product of these, if this product is more, likelihood of observing these things will be more. Now, we look for theta which maximizes this product. So, this is what the philosophy of likelihood is, and this is for density, and of course, for discrete case where you are actually having the probability of each value, then you really do not need to do this very close thing and this density business. You can just there take the likelihood to be just the product of the probabilities themselves. So, if it is a probability mass function p theta, where there is probability of probability of p theta, sorry, p theta, so x1, x2, xn, IID with same distribution x that has now PMF p theta, where PMF p theta of x, PMF p theta x equal to a, or rather a equal to just nothing but probability of x belonging to x being equal to a. Now, this theta determines it, just like we observed in the case of Bernoulli probability. I mean, their probability of x being 1 will be p, where p is the head probability. So, actual value depends on which value you start with for p. If it is p is half, then head probability is just half. If p is 0.5, 0.2, head probability is 0.2, and so on. Now, you have observed this here. You, for the likelihood function, you take the product of these things, because these, now here the interpretation is very easy. There you wanted to take this f theta to be very small, probability of very small neighborhood. Here this is actually the product of the probabilities, probability of x1 taking these values. So, probability of x1 taking a value a1, xn taking value an, and these are IID, these are independent. So, probability of, remember, for independent, probability of the underlying sets are independent. So, probability of having these things will just be probability of having x1 equal to a1 probability xn equal to an. Now, this is, as all these have same probability as theta, it will just be probability of theta a1 probability theta an. Now, for specific values of, and this is true for each xi. So, this likelihood becomes probability theta xi. Remember, we discussed this. So, recall the actual calculation for exponential distribution was done using taking log, often in case of maximum likelihood estimator where you have to maximize the likelihood function, it's very common to, instead of maximizing likelihood function, maximize the log of the likelihood function. So, the maximizing log likelihood is a common technique. And that works because log is a monotonically increasing function. So, wherever likelihood achieves maximum, log likelihood will also achieve maximum. So, this was the problem. You take this exponential distribution and try to find the value of theta based on this random sample, which basically maximizes the likelihood. So, we created this likelihood function, we took the log that simplifies into this thing, and this gives us, once you differentiate it, basically theta hat gives you this critical value, and this gets verified by second derivative test also. One can verify this by second derivative test. So, I stopped there just to give you a philosophy. One can check this second derivative test. So, basically you can do, take del 2 log L del theta square, and you will observe that this becomes this thing. So, basically when you take the likelihood estimated to be, in last page we proved the critical value to be theta bar equal to x bar, the sample mean. If you put theta equal to sample mean, this becomes when you take theta to be sample mean, this becomes, so theta hat equal to x bar implies n theta hat equal to summation xi. So, this will become minus summation xi, which is minus n x bar. But we observed that exponential distribution, if you recall from the density itself, exponential distribution with probability 1, like with exponential distribution, the probability of exponential distribution random variable taking negative value is 0, because it's the density is supported in non-negative real line. So, for any subset of R that which is subset of negative, any portion of the negative line will have probability 0. So, this is your exponential distribution function. For any such place, any such area, probability, call it this probability of x belonging to A is 0, because this is the supported here, the distribution function is supported here. So, that means when you do the maximum likelihood estimation and plug in and get the critical value to be theta hat equal to x bar at that. So, for any random sample, that theta hat, because they are supported in positive line, all the xi's, x bar is also non-negative. So, in particular and a continuous random variable taking just one value has probability 0, because you are integrating. So, xi's, each xi being 0 is just probability xi being 0 to the power x being 0 to the power n, and for continuous, as we observed in fourth lecture, that the probability of taking a particular value is 0. So, probability of xi being greater than 0 for all I is 1. In particular, this gives us that we can safely assume x bar is positive, and if x bar is positive, second derivative gives you minus n, oops, sorry about that. Second derivative gives you minus n x bar over theta cube. Theta is non-negative and minus x bar is non-negative. So, this basically, so if you plug in the s values there, you will get negative. So, now we know that at a critical point where second derivative is negative gives you local maximum. So, this is tells you that this attains maximum. So, this was the example where we ended. We did not discuss the second derivative test, but like the important part is to just know that the second derivative test confirms that this is a maxima, but we observe at the end, like what I mentioned, this is a scenario where unbiased estimator, maximum likelihood MLE of theta is also unbiased. We observed this at the end of last class, because for exponential distribution theta was the mean of the population, and we just saw that by unbiased estimation, by maximum likelihood estimation also, we got the estimator to be theta, to be the population mean. So, I am sorry, for exponential random variable we know that the population mean is theta for exponential theta. MLE method gave us the sample mean x bar to be the maximum likelihood estimator for theta. We also know that sample mean is an unbiased estimator for theta, or rather unbiased estimator for population mean. Now, population mean is theta, so sample mean is also an unbiased estimator for theta. That means the maximum likelihood estimator is an unbiased estimator also in this case. This is where we stopped. Now, likelihood estimation for normal distribution is the next topic that we will move on to. Normal distributions are extremely popular, and as you know, I briefly mentioned this before when we were discussing lecture 4, and you will also see this coming really regularly in this course. So, PDF of normal distribution, normal mu sigma squared, the general normal distribution is given by this. Here you can see that there are two parameters. You know, last time when we were doing maximization, last time for exponential distribution, we discussed that there it is enough to just take derivative with respect to theta, because there is only one parameter. Here unfortunately there are two parameters. So, for maximization you will have to actually find values for both theta and mu, and theta that maximizes it. Well, if you assume one of them is known, then that is a separate thing, then you are back to one parameter, but if both are unknown, you will have to maximize, you have to find values for both theta and you have to find values for both mu and sigma that maximizes the likelihood. So, this is your density function. You take an IID sample, here assume the parameter is a vector parameter, call it theta to keep the same notation as before. So, the likelihood function becomes just the product of these things with x replaced by xi, and then you take product for I running from 1 to n. So, that gives you this expression. In the numerator things just get added, and the denominator you are taking n many of them. So, it just basically sigma becomes sigma to the power n, and square root 2 pi becomes 2 pi to the power n over 2. Now, you want to maximize this likelihood function. As in case of exponential, for maximization you take partial derivatives. If you take partials, well, okay, before partial derivative, here also you take the log likelihood approach. So, you take it simplifies, because whenever there are things in the power, taking log removes the unnecessary exponential thing and just reduces it to a simple polynomial or algebraic expression. Now, you have minus n log sigma minus n over 2 log 2 pi. Observe that this is free of mu or sigma. So, when you are doing derivative, that will vanish. This has mu and sigma both, and this has mu. So, now when you want to find the critical values, you just equate the first partials to 0. Here one can observe that you will basically, when you are doing first partial with respect to mu, you will get sigma square will come out, and because it is just sigma square times this, sigma square will cancel. Actually, you will get an estimator for mu as sample mean. So, this is already even before you are getting to sigma, you are getting an estimate for the mu, that is the sample mean. Now, of course, we have to see this is maximum likelihood estimator or not, because you have to do the second derivative test, but it will be this. And it will be the maximum likelihood estimator. So, basically here also MLE for mu is unbiased as in case of exponential. So, similarly, when you are trying to do it for sigma, you just take this derivative with respect to sigma square, well, not with respect to sigma, but sigma square basically. You will actually get, if you do the second derivative and do the all calculations, guess what, MLE of sigma comes out to be this one. So, 1 over n summation xi minus x bar whole square I running from 1 to n gives you MLE for sigma square, the population variance, not 1 over n minus 1 as in the unbiased case, but 1 over n. Simple second derivative tests will tell you that these estimators are actually, I am not getting into the second derivative test because it is just a cumbersome calculation. So, second derivative test for normal will tell you, this calculation for will tell you these are actually maximum, these are maximum, that will second derivative test will tell you that this is maxima has been attained. So, next we go to another interesting example where derivative technique itself is not used for finding likelihood, maximum likelihood estimator. So, this is interesting because of the technique used. Suppose you are taking uniform 0 theta distribution, where uniform distribution starting from 0, but the top part where the uniform is generally over an interval. So, the left point of that interval is taken to be 0 and the right point has been parametrized by theta. Uniform 0 theta, of course, the PDF will be 1 over theta, that is uniform AB is 1 over, that has density B 1 over B minus A when x is between A and B. So, it is uniform 0 theta, so density is 1 over theta minus 0 whenever x is between 0 to theta. If you take, and it is 0 other outside, so if you take x1, x2, xn uniform 0 theta, what is the likelihood? Well, it is whenever they are, because you are picking them within 0 to theta, they become, all of them are between 0 to theta. So, for all of them has 1 over theta as the PDF value. So, when you are taking product of them, it just becomes 1 over theta to the power n. This is just 1 over theta to the power n. So, the likelihood function becomes 1 over theta to the power n whenever all these values are less than theta. Now, this is captured by introducing this notation of maximum. We call this x bracket n to be the maximum of the x1, x2, xn. All of the xi's have to be between 0 to theta, which is equivalent to saying all of them has to be between 0 to theta. So, it is equivalent to saying the maximum is between 0 to theta. Being less than 0 is, of course, has probability 0. So, the likelihood function here becomes 1 over theta to the power n when xn is between 0 to theta, and 0 otherwise. Now note that what really maximizes it, what value of theta maximizes it. This is your likelihood. Theta can be anything. So, this says basically theta is greater than xn. This is what it says. So, now you want to maximize this for all values of theta bigger than x maximum. Now, bigger the theta gets, worse the smaller this becomes. So, the value that maximizes is this. Hence, the MLE is x maximum. So, one can continue with various examples. I have put them in the notes, few more examples. So, if you have gamma distribution with parameter p and theta, so suppose p is known, you are trying to find maximum likelihood estimator for theta. You take this likelihood function and you differentiate the likelihood function as in the case of exponential. Remember, exponential is merely a special case of gamma. This example I just have put, which is a generalization of the exponential case we are doing, and we are anyway taking p to be known. In case of exponential p equal to basically 1, you just play the same game, you just take the logarithm and you differentiate, you get the maximum likelihood estimator to be x bar divided by p. Again, by second derivative test, one can check that this attains local maximum there. One more example on Poisson. One can take the PDF of the Poisson distribution. This is, or PMF, this is a discrete case, the probability mass function for Poisson. This is what it turns out to be. You take the likelihood, this will just be the product. One can take the logarithm. The interesting part is that, like, however ugly this looks like, if you take logarithm, exponential will of course, so first of all, log AB is just log A plus log B. So, these terms will split, and also this, all three will split, because first these will split and then this and 1 over this will split. So, once now that all of them are splitting, you just have all three terms, but now this is just free of mu. So, you can forget it, you can just play with this and you get that again sample mean is giving you the or maximum likelihood estimator for this mu. And again, through second derivative test, one can check that this attains the maximum. So, one can do it for various other examples, and calculation wise, very simple example will be Bernoulli, our coin tossing cases. You have x1, x2, xn, the likelihood will just be product of these things, which turns out to be the p to the power the sum times 1 minus p to the power n minus the sum. Here, if you differentiate it, simply the sample mean will come out to be the unbiased estimator. I will like to stop my talk here. I mean, I have put one more example of binomial here, which involves some little more complicated calculation. You can see it in the notes. The philosophically it's same. Another estimator, I have put another example from continuous. It's basically doing the same thing. All these examples are done in details in the notes. You can take a look, but I think this is good enough for today's talk. Thank you very much. Thanks for your attention.